So in the previous lecture, we calculated the value of the k, and this value of k was the n pi over L. And we ended the discussion to find out the value of the k because both are the constant which are required for the wave function and simultaneously for the probability density or the density of finding the particle in one dimensional box. And with the k value, now you know all of these parameter. N is the energy of any level, and it may be 1, 2, 3, 4, and so on. Pi is the constant, and L is the length of the box in which it is restricted within one dimension, that is called the x direction. So today we will find out the value of the A, and then our target will be finished with the solution of the Schrodinger wave equation with the particle in one dimensional box. So here, this is the procedure today. This is just the little bit one of the, we will use the mathematic equation and then find out the value of the A. And here assumptions are written over here. The We want to calculate the value of A, so we are going to start with our previous knowledge. And what was that? Because the particle is restricted in a box and having the dimension of 0 to L. So it is starting from the 0 and ending with the total length, that is called the L. And the probability of finding the particle, or you can say the density of the particle or the density of the electron, must be equal to unity, that is indicated over here. So the particle is moving in one dimensional box with the wave, and this we have explained in the previous lecture. It may be sine kx, it may be cos kx, and this is the imaginary, this is the real, and we discussed that uh, and the both real and the imaginary are actually the real functions are over here. And the maximum probability, or when you take the square of this wave function, that will be equal to unity, as it is indicated over here in this diagram. So we are using this formula. So what is this? Actually, this is the normalization process. In mathematics, we call it. So I am going to take the square of the wave function with the differential, with the change in dx, and that will be equal to the unity. As we have said, the maximum, the probability, this is the probability actually. When you take the square of the wave function, and the square of the wave function is called the probability, and this is the maximum probability is equal to 1, and the limits of the box are from 0 to L. So this is just the understanding what we are going to do with the this equation to find out the value of the A. So what is the next step? Where the psi square dx gives the probability of finding the particle between x and x dx. So this is the diagram in which it is shown where is the probability of finding the particle. So actually this is the maximum probability, as is indicated over here, and it is also shown with the dark color over here. And again, this is another probability of the finding the particle over here. So if you want to calculate the probability of finding the particle at any position, so let's say we are assuming at this is the x, and what is the change in x, that is called the dx. So the probability between x and the dx at this region, what would be the probability as indicated with the small arrows? So this is the x, this is the dx. So the probability between x and ds, as it is shown with the blue line, we can calculate by using the simple formula, and the formula is same. So I am just putting the value of the psi and the psi we have already derived from the previous equation, and it is again written over here. So when you take the square of this equation, actually this equation will become like this. So after taking the square of this equation and putting the value of over here, so when you take the square, it will become psi square a square sine square n pi over l x. So this will, when you take the square of this one, it will become sine square, and let's suppose this is the theta, so this will be the sine square theta. So you do not need to, or you take to square of the this figure, but you have to take the square of the sine. So actually sine square mean sine multiplied by sine, so you have to take 2 times the square of the sine, so it will be the sine square of this one. So this is just the how you are going to express, or you are taking the square of the psi function. So I am with the square, I am putting in this equation with the after putting the value of the psi square over here, this equation will become like this. So what is the this equation? This is the a square will be the constant, it will be here. Then you have to take the sine square is there, and n pi lx, n pi lx is there, and dx is coming from the dx, and 1 is coming from the, and the same equation. So in a very simple way, there is no much difficulty to understand the this behavior, and this is very simple equation. I am just replacing the value of the psi in this equation after getting the square, and then this equation will become like this equation. So this is the same equation we derive in the previous slide. Now this is the mathematic formula, because we are going to get the definite integer by using this equation, and this is the general formula. So you first you must understand this one, and then I will move further. So actually when you are using the mathematic formula, this you have to remember, this is the mathematic formula. Similarly, we are using for the integration or the differentiation. So the basic formula you must know, and this is the same as we are using the other mathematical formula. So I am using this one to get the normalization constant, or the value of the a, by using this formula. So this is the sine square a x dx, that will be equal to x is the position, or the what here is the, let's suppose the x axis, the position of the particle on any point at the x-axis. Again, that will be sine 2ax over 2a. Now I am just putting the value uh, of our equation in this equation. So with the limits, we have earlier decided that the limits are x from L is the maximum value. I am written over here in reverse, and x is the starting from the 0 and ending with the L. So whenever you express the limits on the this is the integration sign, so it will be starting from the low limit to the high limit, so starting from the 0 to L. So that's why the limits are from x L to x0, because you have to subtract, the first will be the higher value and the second will be the lowest value. So when you put the values of the x equal to L and x equal to 0 over this equation, so that means the first value is the higher, that means this x is equal to L, and this x will be equal to 0. So when you put the x, the value of x over here, that is the L, this will become L by 2 minus, so this is the sine square a, and here the value of x is 0. And again, if the value of x is 0 over here, this whole value becomes 0, and the sine 0 will be equal to 0. That means the only the definite integral of this equation by putting our limitation over here, the value of the this whole equation will be L by 2, and that's why it is written over here. This is the value of the L by 2, and this is the same because why I'm using this one, because this equation is similar to this equation. So our just the variable is the x, and that is having the limits from 0 to L. So after putting the value of the both over here, so this is whole equation will become 0, and this is the L divided by 2, and this is coming out L divided by 2. A square is the constant, equal to 1 is coming from the equation. So with the definite integral of this equation by using this mathematical formula, uh, this equation will become like this: a square L by 2 equal to 1. And when you want to get the value of a will be, you have to multiply by 2 and divided by L, and then you take the under root. With the under root, a square under root square is cancelled out, and this will be the value of the a, that will be equal to under root 2 over L. So this is the actually what we are getting the normalization process. This is called the normalization process, and this is the value of the a. Now, this was our previous equation. When we just put the value of the k in the first equation, and now we have calculated the value of the a, and the value of a is 2 over L under root. So I am just putting the value of a over here. So this psi will become equal to under root 2 over a sine n pi over L and x, and this factor is called the normalization constant. So actually we have achieved the final target, and here if you want to calculate the wave function equal to 2 over L sine n pi over L and x, and here the value of the L, and the 2 is the constant, and you also know the value of the n, whatever you are calculating for the energy level 1, 2 and 3, so on. I will later discuss this diagram. Now this is called the wave function, or you can say this is the probability amplitude. So probability amplitude, how much the amplitude of the wave is there. So wave is starting from here, amplitude is increasing, it goes to the highest value, then the amplitude is going to decrease. So actually at any point you can calculate the probability amplitude, and with this one you can calculate the what would be the wave function at any of the energy level. And the second important point is that is giving you the electron density. So where is the probability density or the maximum density of finding the electron when this electron is moving in a one dimensional box and having this wavelength, and by using very simple way of the calculation, I am just getting the square of the psi, and the square of the psi is the probability density. When you take the square, this will psi will become psi square. 2 over L under root square is cancelled, it will become 2 over L, and this is the sine square because you are taking the square of this one. So this is the just the by taking the square of the sine, you can find out the probability density, or the density of the electron at the any of the position over here with any of the energy level. So first look what we have the wave function and the probability density. Later on in one of the separate lecture, we will be calculating the wave function and the probability density. And here just to differentiate between these two important parameter psi and the psi square. So the first, this is again the limit of the box, wall 1, and this is the wall 2 starting from x0 to xl. So let's suppose this is the energy level 1. So when there is, this is the energy level, so here just there are two wave functions are given. So here when n is 1, that is when the first energy level, this is the wave function for the first energy level, and this which is indicated over here with the blue color, this is the wave function for the second energy level. So n1, and this is for the n2, with the probability density or the density of finding the electron. When you take the square of this one, so this wave functions becomes like this. So what is the difference over here? So again, actually this is the wave function for the energy level 1, and this is in a this color, this is the energy level of 1. And for the energy level 2, when n the value of 2, this was the wave function, and this is the probability density of the second energy level. So if you keenly look at the what we have actually done over here, this factor actually this is the which is the wave function in the minus, it is going to be the positive, it is moving up. So actually when you move up, this will become like this. So that is only the way of expression between the wave function and the probability density. So how can you find out the probability density? This is indicated over here with the dark shade over here. So as we have earlier said, the when the wave is, let's suppose this is the wave of the first, and this is the probability density expression over here. And what would be the maximum probability of the electron? Maximum probability of the electron is over here, and that is indicated with the this color, and because this is the energy level of the first first energy level or the first shell, and this is the second energy level, and the maximum probability of the electron would be here, and another position is here. So there are two position in the second energy level where you can find the maximum probability of the particle, and this is over here and here, and this is also indicated with the shades. Here you can find the electron, and here you can also find the electron. So this is the representation of the wave and wave function and the probability density of a particle in one dimensional box. So with this Schrodinger equation, actually now you can calculate what is the probability amplitude of the wave, and what would be the density of the electron at any energy level. And this is very, very important. And actually you will learn more when we do some sort of the exercise in one of the lecture in future. So with this, I'm going to end the lecture. So these are our important conclusions, and we will be carrying these conclusions to further discuss in the coming lectures. The first one is the kinetic energy of the particle is quantized according to the equation, and this we have actually derived in this uh, 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 when we were deriving the equation for the particle in one dimensional box. And separately we will also actually I think we have calculated also derive separately this equation, and later on we will calculate the kinetic energy by using this equation. And the difference in the kinetic energy between any of the energy level, that was from energy level 1 to 2 and so on. Here the only difference unknown parameter is the m, and that n is the energy of any level, and the rest of the parameters are the constant. So in the quantization energy, kinetic energy, we have already derived this equation, And this is the important conclusion over here. The particle in one dimensional box, that means the energy is also quantized, so there is no that means it is not unquantized. So similar to the photon or the quanta of light. And now you have learned that the energy is also and particularly the kinetic energy is also quantized in a similar way as the photon according to the Planck constant is quantized. Second important conclusion is over here: the lowest energy is not zero, but it is equal to this whole factor h square over 8 ml square. And the lower energy level is the when you have the energy level 1, because the value of n is equal to 1 2 3 and so on. So when you put the value of 1 over here, so this equation will become h square over 8 ml square. So this is important to note that the energy of the lowest level should not be equal to zero, but it is having this factor or this value. And this 0 point energy can be accounted for by the Heisenberg uncertainty principle. And this is the explanation written over here. Let's suppose if the particle possesses zero kinetic energy, if it is having the zero kinetic energy, then the velocity should also be zero because the particle is not moving. Kinetic energy is half mv square, and when the kinetic energy is zero, then the velocity would also be zero, and consequently there would be no uncertainty in determining its momentum, because the momentum is the mass into velocity. So when there is the particle kinetic energy is zero, velocity is zero, then there is of course no uncertainty in the momentum according to the Heisenberg uncertainty principles. So these are the two important conclusion over here. So with this, I am just ending this lecture, and I will take your questions over here.